A comet near the sun just exploded in brightness, its tail now fanning wider than 5 full moons. Just days later, the sun unleashed its most powerful flare in months, blasting a wave of plasma straight toward that same comet. Now, that comet, R2 Swan, is heading toward Earth, fast. In a few short weeks, it will make its closest pass just as an interstellar object aligns with it in the sky. What happens when a cosmic visitor meets solar fire? Let's explore this together.
First light, the outburst begins.
So, how did this all start? It began quietly. On September 12, 2025, a comet designated C/2025 R2 Swan made its closest approach to the Sun, a point known as perihelion. At first, everything seemed normal. It was a faint object, gradually brightening as expected, with a magnitude hovering around 7.4. But comets are unpredictable. 2 weeks later, on September 26th, amateur astronomers in Japan and Australia noticed something extraordinary. The comet's brightness suddenly surged, jumping by nearly a full magnitude to 5.7. This pushed Swan into naked-eye territory for anyone under dark skies. That's not just a minor flicker, it's a sign of a violent event. This kind of outburst points directly to the comet's nucleus, a frozen core of ice, dust, and rock. As it swung away from the sun, intense solar heating likely caused pockets of supervolatile ices, like frozen carbon monoxide and carbon dioxide, to sublimate and burst through the crust. This process, known as cryovolcanism, flung tons of dust and ice into space, dramatically swelling the cloud of gas and dust around the nucleus, called the coma. Cometary scientist Dr. Casey Liss of the Johns Hopkins Applied Physics Laboratory notes that such events provide invaluable data on the pristine, deep-frozen materials from the birth of our solar system. The event put the entire astronomical community on alert, transforming Swan from a routine object into a live and unpredictable scientific experiment.
Anatomy of a tail.
What does it really mean for a comet's tail to be wider than 5 full moons? Let's put that into perspective. We're not talking about a small, fuzzy patch in the sky. This is a massive structure, stretching over 2.5 degrees, which translates to a physical length of millions of kilometers. For observers, even in suburban areas, this makes it a stunning sight in binoculars. A comet actually has 2 distinct tails. The first is the dust tail, made of heavier particles pushed back by the pressure of sunlight itself, giving it a yellowish-white glow. This tail curves gracefully as it follows the comet's orbital path. The second, and often more dramatic, is the ion tail. This is composed of gases that have been ionized by the sun's ultraviolet radiation, creating charged particles like carbon monoxide ion CO+ that glow with a distinct electric blue light. Because these particles are electrically charged, the ion tail is sculpted by the solar wind and its magnetic field, always pointing directly away from the sun. With Swan's tail being so expansive, even small telescopes can reveal incredible details. Knots of dust, shifting streamers, and sudden kinks. Amateur astronomers are already capturing these changes, creating time lapses that show the tail evolving hour by hour. This massive, unfurling tail isn't just for show. It's a giant, sensitive windsock in space, about to get hit by a solar storm.
The sun awakens.
Just as Comet Swan was putting on its show, the sun decided to join the party. On September 28th, after weeks of relative calm, the sun erupted with an M6.4 class flare, its strongest in months. Solar flares are classified by their X-ray brightness, and an M6.4 flare releases an X-ray flux of 6.4 times 10 to the -5 watts per square meter. Instruments aboard the GOES 18 satellite, which constantly monitor the sun, detected the spike in near real time. Scientists at NOAA's Space Weather Prediction Center, or SWPC in Boulder, Colorado, immediately began analyzing the event. They used data from other observatories like NASA's Solar Dynamics Observatory, or SDO, to pinpoint the flare's origin, a magnetically complex sunspot group designated Active Region 4232, which had a beta-gamma-delta magnetic configuration, a known precursor to powerful eruptions. Here's the crucial part. This active region was located in the same quadrant of the sun that Comet Swan was moving through. Within minutes, The flare was followed by something even more significant: a coronal mass ejection, or CME, which was confirmed by coronagraphs on the SOHO spacecraft. According to space weather physicist Dr. Tamitha Skov, this alignment presented a perfect natural laboratory.
Plasma on the move.
So, what is a coronal mass ejection? Well, it's a massive eruption of plasma and magnetic fields from the sun's outer atmosphere, the corona, releasing billions of tons of material into space. Think of it as a solar cannonball. This particular CME shot out from the sun at a speed estimated between 800 and 1,000 kilometers per second. Forecasters at the NOAA Space Weather Prediction Center quickly began running its trajectory through their WSA-NLIL model, which is a pretty sophisticated computer simulation that predicts how solar disturbances travel through the solar system. Using data from coronagraphs on satellites like the Solar and Heliospheric Observatory, or SOHO, which create an artificial eclipse to see the sun's faint corona, they determined the CME was not aimed at Earth. Instead, the models showed its path would sweep directly through the sector of space occupied by Comet Swan. The timing was remarkable, just 2 days after the comet's major outburst. This set up a rare opportunity for scientists to watch what happens when a powerful solar storm collides with a comet. The plasma density in the CME, while incredibly thin by earthly standards, is more than enough to overwhelm the comet's own magnetic field. The question for forecasters was no longer if the CME would hit, but when and how dramatically it would affect the comet's enormous, newly expanded tail.
Magnetic scissors.
Here's where the physics gets fascinating. A CME doesn't just blast through space. It carries with it a tangled web of magnetic field lines from the sun. A comet's ion tail is also governed by magnetism. The charged particles of the tail are essentially clinging to invisible magnetic tethers that stretch for millions of kilometers. The real drama happens when the CME's magnetic field collides with the comet's magnetic environment. If the magnetic field embedded in the CME has an orientation that is opposite to the comet's field, a southward BZ component in space weather terms, it can trigger a process called magnetic reconnection, a concept first theorized by physicist Hannes Alfvén. Think of it like a cosmic short circuit. The magnetic field lines from the CME and the comet's tail can snap and violently reconfigure, releasing a tremendous amount of energy and accelerating particles in the process. In practical terms, this process can act like a pair of magnetic scissors, literally severing the comet's ion tail. This causes a whole section to break off and drift into space, while a new one begins to form almost immediately behind it. This spectacular phenomenon is known as a disconnection event.
The forecaster's puzzle.
Predicting the outcome of this cosmic collision is a huge challenge. While models showed the CME heading toward Comet Swan, solar ejections don't travel in perfect straight lines. They expand and can be twisted by the ever-present solar wind. The best estimates from the SWPC place the CME's arrival at the comet between 48 and 72 hours after it left the sun. The key uncertainty was whether the most intense part of the CME, with a strong southward BZ component, would score a direct hit on the ion tail. Without a direct impact on Earth, scientists have limited in situ data. However, data from spacecraft like NASA's Stereo-A, which observes the sun from a different vantage point, helps create a three-dimensional picture of the CME, improving the forecast. Dr. Carl Battams of the U.S. Naval Research Laboratory, a leading expert on comets observed by SOHO, noted that these events are nowcast situations, where data is analyzed as it arrives with little room for error. Every major forecast center flagged the event for comet researchers worldwide. For Earth, the risk was zero. For Comet Swan, however, the incoming plasma was a loaded gun. The world's astronomers were now watching, waiting to see if the tail would simply ripple or completely break apart.
Citizen science mobilizes.
This is where the story gets really interesting, because it's not just professionals in sterile control rooms who are tracking this. A global network of citizen scientists, amateur astronomers with backyard telescopes and cameras, is playing a crucial role. Because a tail disconnection event can happen fast potentially in as little as 90 minutes, continuous observations from around the world are essential. As the Earth rotates, observers in one continent can hand off the watch to the next, uploading their findings to platforms like the Comet Observation Database, or COBS. They are documenting everything, using techniques like astrometry to precisely measure the comet's position and photometry to track its brightness changes down to 1/100th of a magnitude. Organizations like the American Association of Variable Star Observers, or AAVSO, help coordinate these campaigns, ensuring standardized data collection. Their data is vital because it can provide a high-cadence, 24/7 record of the event as it unfolds. By pooling their observations, this global team is building a unique, real-time record of a rare cosmic interaction, proving that in modern astronomy, anyone with a clear sky and a camera can contribute to a major scientific discovery.
The perfect alignment.
As if a dramatic outburst and a solar storm weren't enough, the cosmos has thrown in another twist. On October 21st, 2025, Comet Swan will make its closest approach to Earth, passing just 0.26 astronomical units, or about 39 million kilometers away. This close pass is remarkable for another reason: the timing. It occurs during a new moon, meaning the sky will be at its darkest, providing perfect viewing conditions. And there's more. On the very same day, an interstellar visitor, designated 3I Atlas, will be in the same general region of the sky from our perspective. While separated by millions of kilometers, this alignment offers a rare chance to compare a comet from our own solar system with an object like 2I Borisov, which had a distinctly different chemical composition. Such alignments are invaluable for testing our models of solar system formation and planetary science. The geometry of Swan's close approach also enables a cool trick for amateur astronomers: the parallax effect. Because the comet is relatively close, its apparent position against the background stars will shift measurably when viewed simultaneously from different locations on Earth, allowing backyard observers to triangulate its precise distance.
Southern skies spotlight.
So, how can you see this celestial drama for yourself? For the next few weeks, observers in the Southern Hemisphere have the best seats. From places like Australia, South Africa, and South America, Comet Swan will be high in the pre-dawn sky. To find it, you'll want to look toward the southern constellations of Grus and Piscis Austrinus. An easy guidepost is Fomalhaut, the brightest star in that area of the sky. As October progresses, its position will improve for those in the Northern Hemisphere as well. The comet's massive tail, stretching over 2.5 degrees, makes it an excellent target for binoculars. A standard pair of 7 by 50 binoculars can likely frame the entire tail in one field of view. For photographers, a DSLR camera on a tripod with a lens around 50 millimeters, set to an ISO of 1600 or 3200 and a 10 to 15 second exposure, should capture a beautiful image. You can use free software and apps like Stellarium or Sky Safari to generate a precise star chart for your exact location and time. This is your chance to witness a rare cosmic event firsthand and even contribute to science.
Cosmic forces collide.
Let's bottom line this. We have a documented encounter between a powerful solar storm and a comet that has recently undergone a massive outburst. Scientists are eagerly waiting to see the effects of the CME, reminiscent of the 2007 event, when NASA's Stereo spacecraft watched a CME completely rip the tail from Comet Encke. Dr. Geraint Jones of University College London, who studied that event, emphasizes that these collisions allow us to probe the comet's invisible magnetic environment. However, it's crucial to note that the exact outcome for Swan remains to be seen, and no direct link has been scientifically established between the M6.4 solar flare and Swan's earlier outburst. The timing is likely a spectacular cosmic coincidence. What is certain is that this October provides an unprecedented window for both professional and amateur observers to witness the dynamic interplay of cosmic forces in real time. Key questions remain. How much material will be stripped from the tail, and what can that tell us about the comet's composition and the sun's power? The journey of Comet R2 Swan is a rare and unfolding story. A live experiment in solar system physics happening right before our eyes. The universe has once again reminded us that it is a dynamic and unpredictable place. From a sudden cometary outburst to a perfectly aimed solar storm, the saga of Comet R2 Swan is a testament to the powerful forces that shape our solar system. Whether you're an astronomer with access to a powerful observatory or a curious sky watcher with a pair of binoculars, the next few weeks offer a front-row seat to this spectacular celestial event. Go outside, look up, and be a part of the discovery. Don't forget to like, subscribe, and hit the bell icon. Thank you for watching Future Facts.